Welcome back. So now I'm going to show you that the dot product is very useful when you work in 3D. So here you have a beam. This thing is ground, and this is where the beam touches the ground. And the tip of the beam is right here where the origin of this coordinate frame is. And so you can go from the tip of the beam till the ground of the beam. If you go 2 meters along the x-axis, 2 meters along the y-axis, and 1 meter along the negative z-axis. Let's call this point O and this point A. And now a force is applied to the tip of this beam. In the xyz coordinate frame, this is your force vector. And now my question to you is, what's the component of this force along this beam? Try this problem out by yourself first, and then let's see the solutions in the next video. Thank you very much. Welcome back. So this is where the dot product is very useful. You have the xyz components of the force vector, and you want to get the component of that vector along this beam. And so in order to do that, you first want a general unit vector from the point where the force is applied, so from the tip of the beam. Let's call this general unit vector UA with respect to O. So in the A direction from O, the position vector of A is this one. The magnitude of this vector is this one here. It's 3. So this unit vector equals this one, which eventually gives you this thing here. So that's your general unit vector. And now the force vector in the A direction with respect to O, it equals F dot and this general unit vector. And since the result of the dot product is a scalar, then what you will get here is the magnitude of this force vector. So this is your force vector dot your general unit vector, and in the end you will get 0.667 newtons. And so this component here, that's the component that goes along the beam. So you see, using the dot product, you were able to obtain it very easily. With one dot product, you were able to obtain this component along this beam. Thank you very much. Welcome back. Earlier we had a tower problem, and in the second tower problem, I asked you if I wanted to have a resultant force applied to this point D by these 3 cables, if I wanted it to be like this, meaning that I wanted this FR vector point down along this tower, if this is the result that I wanted, then what kind of tensile forces did you have to have in those cables? And we found that FA with respect to D had to be 117 newtons, then FB with respect to D had to be 1129 newtons, and then FC with respect to D had to be 466 newtons. And then we also had a requirement that the maximum tensile force in those cables was 900 newtons, and because of that, this cable from D till B would obviously break. But for now, let's forget about this one. Let's assume that our cables are able to cope with these tensile forces. And just to remind you that the general unit vector A with respect to D, it was this one. The general unit vector B with respect to D, it was this one. And the general unit vector C with respect to D, it was this one. We calculated them earlier in the previous videos when we solved this tower exercise. And now, what I would like you to do, I would like you to perform a reverse operation, but using the dot product. So I would like you to take these three forces, and I would like you to use the dot product in order to obtain this resultant force again. So how would you do it? Try it out by yourself and then see the solutions in the next video. Remember, you need to go from these three forces to this resultant force using the dot product. Okay? Good luck. Welcome back. So let's now obtain this resultant force using the dot product. Essentially, what it means is that we have to take these three forces here and we have to project them onto the line that is parallel to the tower. For that, we need a general unit vector that goes from D along the tower down in the direction of O. In other words, this unit vector would be in the direction of O with respect to D. It equals 0i plus 0j minus 1k. It makes sense, right? You go from D along the tower down, but since it's a general unit vector, its magnitude is 1, but since you're only using the k component and you go down, then you have to have minus 1 here. And so you have to take these three forces and project them onto this general unit vector. In order to do that, you first need to take these three forces and decompose them into their I, j, and k components. So you take the magnitude of Fa/d, which is this one here, and you multiply it by the unit vector A/d. That will give you this vector, but in the I, j, and k component form. And once you have that in this form, only then you dot it with the general unit vector that goes down along the tower. Then you obtain the component of this force vector along the tower. Now this vector here in the Cartesian form, it's this one. So essentially, your magnitude was 117, and then this vector here, well, that's this one here. And then you dot it with this unit vector, and you have this result here, 80.9 newtons. Here I'm just doing the dot product. And again, this result is scalar. You can see that since this unit vector here, O/d, only has a k component, because of that, in the force vector, only its k component contributes to the final result here. And so what is this 80.9 newtons? It's the component of this force here that goes down along the tower. Let's do the same thing with this force, Fb/d. I multiply its magnitude by this general unit vector, which is this one here, and which points in the same direction like this FBD vector. So with that, I decompose this vector into its I, j, and k components. That's what I do here. And then I dot it with this unit vector that is in the direction of the tower, and in the end, I get this result here. Again, this is the component of this force, B/d, along the tower. And finally, let's do it with this force, C/d. This is its magnitude. I multiply it by this unit vector, which is this one here, and then I get the same force, but in the Cartesian form, and then I dot it with this unit vector, and then in the end, I get this result here. So this is the component of this force along this tower. And now, I will just add up these three components. So I have this one, which is this one, plus this one, which is this one, plus this one, which is this one here. and that will give me 1489.9 newtons, or I can approximate it to be 1490 newtons. So essentially, if I had approximated this one to be 81 newtons, then here I would have had 81, and then I would have received this answer right away. It's just we had some approximations along the way. And you see that using the dot product, again, we achieved this resultant force, which is exactly the resultant force that we started with. As you can see, in 3D it was very easy to do using the dot product. Thank you very much. Welcome back. I have two vectors here, F1 and F2. You can see that their magnitudes are the same. To represent the direction of F1, I'm going to use the spherical coordinate system. So I'm going to say that theta 1 equals 340 degrees and phi 1 equals 35 degrees. So it's a spherical coordinate system. By now you should already know what it means. So I don't have to draw it here. You know which axis you need to measure your theta from and which axis you need to measure your phi from. And then the direction of F2 is represented with the coordinate direction angles. So alpha 2 equals 45 degrees, beta 2 equals 60 degrees, and gamma 2 equals 120 degrees. So these are coordinate direction angles, and again, by now you should know how to read them. So I don't have to draw them here. And now, my question to you is, what's the angle between these two vectors? Let's call it psi. Using all this information, can you give me the angle between these two vectors? Can you give me psi? Hint, use the dot product. If you use the dot product, then it will be very easy to find psi. So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now calculate this angle psi. It turns out that the dot product has another useful application. If I have two vectors and an angle between them, then you already know that A dot B equals the magnitude of A times the magnitude of B times cosine theta. And that means that you can write cosine theta equals A dot B divided by A times B. So this is a scalar and this is a scalar. And so theta equals inverse cosine and then this ratio here. And that's how you find this theta. Now that's in 2D, but the great thing about dot products is that you can also work with them in 3D. And so this is a three-dimensional problem, but you can still find psi using the same concept. So let's first decompose our F1 and F2 vectors. So from the previous videos, you know that if you have this spherical coordinate system, then your F1 vector can be decomposed like this. This is the magnitude of this F1 vector. This is the general unit vector in the direction of that F1 vector. These are the phi angles. Then these are the theta angles. And these are your I, J, and K components. So your F1 equals this one here. And then from the previous videos in this section, you also know that F2 equals this one here. Again, this is the magnitude. This is the general unit vector in the direction of F2. Then this is alpha 2, this is beta 2, and this is gamma 2. And these are your I, J, and K components. From that, you know that F2 equals this one here. And then you know that F1 dot F2 equals the product of their magnitudes times cosine psi. So this one is 400 times 400. Essentially, it's 400 squared. And then this one here, that's F1 dot F2. Remember, I don't have to use I, j, and k components all the time. I can also use column vectors. And so I will have this one times this one plus this one times this one, and then plus this one times this one. And so that will give you minus 20172 newtons squared. Because remember, now we are not dotting an F vector with some kind of unit vector. The units of a force vector are newtons, and then the units of a unit vector were dimensionless. As a result, you would get some kind of force, and then your unit would be Newton. That's what we did before. But now we are multiplying two force vectors together using the dot product. So you see that you have F1 times F2 times cosine psi, but this is just some kind of ratio. It's a dimensionless ratio. If we take this right triangle, here you have 90 degrees, then this would be A over C, and then the units would be meters over meters. In other words, it's dimensionless. But here, since you're multiplying two force magnitudes together, then you have newtons times newtons, or in other words, newtons squared. And then, well, you know your dot product for these two force vectors. You know their product of their magnitudes. Therefore, you know that cosine psi equals F1 dot F2, and then here I multiply their magnitudes. In other words, I have this number, Newton squared, divided by 400 squared, Newton squared. And so here, the Newton squared will cancel out, and I will have a dimensionless ratio, which is what I should have for cosine psi. And now, psi equals inverse cosine this ratio, and the answer is 97.2 degrees. There you go. You have found your psi angle, the angle between these two force vectors, using the dot product, and it's 97.2 degrees. Thank you very much. Welcome back. Let's do one more problem. We have a rod here that goes from the origin till this point here, and this rod is used to hold a flag. And here in gray, you have a wall, and this rod is held in place by these two cables. And you can see all the dimensions here. We can call this point here A, then this point B, and this point C. So in order to go from O till A, you have to go 4 meters in the positive Y direction, and then 3 meters in the positive Z direction. In order to go from O till B, you have to go 1.5 meters in the positive X direction, and then 6 meters in the positive Z direction. And in order to go from O till C, you have to go 2 meters in the negative X direction and 4 meters in the positive Z direction. And now the question is, what is the angle from the cable that goes from A till B until this rod? So let's call this angle theta. Then what's the angle from this cable that goes from A till C until this rod? Let's call this angle phi. And then what's the angle between these two cables? Let's call it gamma. So try to find these three angles using the concepts that you have learned so far. Try doing it by yourself first, and then I'll show you the solutions in the next video. Thank you very much. Welcome back. So let's now find these three angles. It will be very easy to do using the dot product. But first, I need three displacement vectors. RO with respect to A. So that's the vector that starts from A and it goes till O. So this is the vector that I want to have. Then I want to have a displacement vector B with respect to A. So that's essentially this displacement vector here. It goes from A till B. And then I want a displacement vector C with respect to A. That's this displacement vector. You go from A till C. You can right away imagine that you have this shifted coordinate frame here. This is X apostrophe, Y apostrophe, and Z apostrophe. And so you make your measurements from here. And so in order to get from A till O, in terms of X direction, you don't have to go anywhere. They have the same X value, so 0I, but then you have to walk 4 meters in the negative Y direction, so it's minus 4J, and then you have to walk 3 meters down, or in the negative Z direction, so it's minus 3K, and that's in meters. Then in order to go from A till B, you first have to walk 1.5 meters in the positive X direction, so 1.5I, then 4 meters in the negative Y direction, minus 4J, and then 3 meters up in the positive Z direction. That's because here you are at Z equals 3 meters, but you have to get to Z equals 6 meters. So essentially you have 6 minus 3 equals 3. And so you write plus 3K. And that's also in meters. And then to go from A till C, you first have to go 2 meters in the negative X direction, so minus 2I, then 4 meters in the negative Y direction, minus 4J, and then you're already at Z equals 3 meters, and you have to get to Z equals 4 meters, so 4 minus 3, that will give you 1. So you have plus 1K. Again, it's in meters. And now you also want to have their magnitudes. The magnitude of RO slash A, that's 5 meters. The magnitude of RB slash A, that's 5.22 meters. And then the magnitude of C slash A, that's 4.58 meters. You get them by simply using the 3D Pythagoras theorem. And then you do what you did last time. You can dot two vectors. It equals this one, and then theta would be inverse cosine, and then this ratio here. So this was a general formula. And so now, in order to find this theta here, I will have theta equals inverse cosine, and then here I will have RB with respect to A dot RO with respect to A, and then I have the product of their magnitudes. And if I make the calculations, then I will have cosine inverse, and then here I will have 7, here I will have 5.22 times 5, and I will get 74.4 degrees. Then phi equals inverse cosine, and now you dot these two vectors, C slash A and O slash A, and you multiply together their magnitudes. And so you have inverse cosine, and then you have 13 over 4.58 times 5, and that will give you 55.4 degrees. Note that since you're multiplying together two displacement vectors, then here you will have meter squared, and also here you will have meter squared. And then when you divide them, then the meter squared, they will get cancelled. So here you will have a dimensionless ratio, which is exactly what you need for your inverse cosine. And then finally, gamma equals cosine inverse. Now you dot these two vectors, b slash a and c slash a, and then you multiply together their magnitudes, and so you will have this ratio, and that will give you 48 degrees. So in order to calculate gamma, you have to take the dot product of these two vectors. Then, in order to calculate theta, you consider these two vectors for your dot product, and then to calculate phi, you consider these two vectors for your dot product. And so, as you can see, the dot product can be pretty useful when you work in 3D. Thank you very much.